Okay, we're going to do problem 12 in the chapter 6 assignment. We're looking at a manufacturing problem where the process has a mean of 11 ounces, standard deviation of 0.1 ounces, and we're told that the process is in control as long as we don't go beyond plus or minus 1.25 standard deviations. So if we are less than 10.875 or greater than 11.125, then those parts are considered to be defects. So we want to know what's the probability of a defect. So for this problem, you should use your statistical toolkit. So open up the Excel Stats toolkit, right-click on the area between the two small arrowheads in the lower left-hand corner. Scroll down until you find the normal probability sheet. So this is the tool we're going to be using. Since we are using the population information for the normal probability distribution, we can go with the mean of 11. We're told the standard deviation is 0.1, and we're looking at an x on the lower end. Let's just use the lower end x of 10.875. Now, to illustrate what I'm doing, I've created a very crude sketch of this probability distribution problem. We have a mean of 11, and we're told that if we go outside of 10.875, less than that, or greater than 11.125, greater than that, then we have a defect situation. And as you can see, these regions are equally distributed around the mean. We go 1.25 standard deviations in either direction to get these values. So the areas that I've shaded in red represent the defect areas, and even though they don't look that way in my crude drawing, these areas are equal. So if we find the area under the curve in the red region to the left, multiply that by 2, then we'll have the probability of a defect in this situation. So if you look at the upper table, the probability of being less than that x value, the 10.875 that I input, is 0.10565. If I multiply that by 2 to have the area under the curve in the 2 shaded regions, that will give me the probability of a defect. So that probability multiplied by 2 gives us 0.2113. So if we had 1,000 parts that we were producing, we would expect to have 211 defects. And in this case, we round down. So the 0.2113 multiplied by 1,000 gives us 211. In part B, they tell us that we're reducing the standard deviation to 0.08, but the limits of our defined defects will be the same. So now they want to know what's the probability of the defect to 4 decimal places, given this smaller standard deviation. So this is intended to demonstrate the importance of the standard deviation in a normal probability problem. So we've changed the standard deviation to 0.08. In our tool, it gives us a probability in this lower tail, the tail to the left, of 0.05909. multiplying that by 2, which I've just done over here, gives us a probability of 0.11817. So obviously, if we can reduce our variation in the production of our parts, then it reduces the probability that we're going to have a defect, all else being equal. So entering in that new probability, 0.1182 then, rounded to 4 decimal places, tells us that the production run of 1,000 parts should only have 118 defects. So compared to the 211, that's a significant decrease in the number of defects, which is the answer to C.